Hello, in this video we're going to look at some advanced topics in math. Now this is the first of three topics we're going to look at. First is integration, then we're going to look at complex numbers and matrices. So make sure you have your integration booklet out, and we're going to begin with an interesting investigation. So our motivation for this section is going to be, how would we determine the area of the unit circle? Well, here we have a grid, and we're going to use this grid to get an estimation, a rough approximation for what the area would be. We're not going to use any formulas, we're just going to try to use some basic estimation. Now, if you look here, we have, of course, a grid, and each one of the grid lines is a half. So if this is 1/2, and this is 1/2, then the area of one of these little grids is going to be 1/4, a half times a half. And that's from the basic definition of area. Area for a square is length times width, or for a rectangle is length times width. And we have to use that piece of information. So the area of this would be 1/4. Now, what we're going to do is count how many squares we have inside of the circle. So we've got, clearly this one is completely in, and this one, and this one, and this one. So we've got 4 squares there. Now, we're going to need a bit of estimation because all the other squares are not fully inside of the circle per se. So we need to have some kind of comparison, and I would probably cut it like this. I would say, if you look here, I think that this whole section is roughly a square, right? We're missing a little bit here, but then we've got a little bit of extra there, and roughly you could probably smush those together and call this over here number 5. I think the same thing here, you could probably call this top part 6. I'm going to do a little other smushing here, so let's call this 7 and 8. So let's just do that all the way around. 9 and 10, 11 and 12. So again, this is not completely true, right? This is an estimation, approximately how many squares are contained inside of this circle. Now, certainly it's got to be less than 16, because if you notice, 4 by 4, all of the squares on the grid are 16 squares. So it's going to be less than 16, and it's going to be, well, more than 4, because there's clearly just 4 in this portion here. So somewhere between 4 and 16, and I think a good estimation is probably about 12. So now to do the area would be equal to 12 squares, where each square has an area of 1/4, which gives you 3. So 3 would be, you could say if you want, units squared. This is the area. Now, hopefully we know the area of the unit circle, but if we don't, maybe this seems like a decent estimation, 3. Let's go ahead and try with a finer grid. So here we have the same unit circle, but we've gone ahead and made each one of the squares, if you look, there are 5 squares, so each one of these is 1/5. And this is 1/5, giving the total area of one of the squares 1/25. So area is 1/25. So go ahead and give it a whirl, try to count up how many squares we have here. Pause the video and give it a good estimation for how many squares are in this unit circle. So hopefully you gave it a try. This is what I came up with for my estimation. So I decided to focus on counting just the squares in the top half of the circle, and then I was going to double up my count when I got to the bottom. But when I got to 39 and 40, I wasn't really able to find anything left over to add to these missing portions, and so I feel like I honestly probably got about 39 and a half. There could be some from this square that you could take off and put to make a full 39 there, but then you'd maybe have a half square left over. So I think I got the following. So I'd say I had 39.5 squares. So I've got to double that up because I had a whole circle. So 39.5 times 2 will be 79. Times 79 by 1/25, because that's the area of each square. So 79/25, which, if you put it as a decimal, is, believe it or not, 3.16. Interesting. I wonder what we'll get if we do an even finer grid. Well, let's go ahead and use this grid to get an even better estimation. Now notice here for each square we have, each square is going to be equal to, it looks like 1/10 times 1/10. So now we're being very precise with our estimation because we can count squares that are 1/100th of a unit. So again, pause the video. In this case, I would recommend maybe just count the squares in the upper right quadrant. So just the squares here and just the squares here. And then we're going to go ahead and multiply it by 4 just to make your math a little bit easier. Alright, so hopefully you've come up with an estimation. When I count all these squares, I come up with approximately 78 little squares. So, to find our estimation for area, we would get the area is 4 times 78 times 1/100, which gives you 3.12. Interesting, interesting. Well, what is the true area of the unit circle? If you remember from your probably grade 9 or grade 10 class, the area of a circle is equal to pi r squared. And so the area of a unit circle would be equal to pi times 1 squared, which would just be pi, or about 3.14. So pretty close because we had estimations of 3.12 and 3.16. So we figure the value of the area should be somewhere around 3.12 or 3.16, which is definitely what we find with 3.14. But how do you know? How do you know this is the true area? How do you know that this formula is correct? I mean, sure, your teacher gave it to you in grade 9 or grade 10, but how do you know they weren't lying to you? How did they even know they had the truth? And so what we're going to do is develop this concept of integration, because integration can be used to find areas and to find formulas like this for shapes like circles or any shape really. And so we're going to start with finding the area under a curve like a function like this. How would you find this section of area? And the idea for integration is just like we did with our square example. What we're going to do is instead of finding the area first, we find a similar question. We calculate the function at a few points, maybe here, 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 and here, and we create little rectangles. In this case, we don't just create squares, we draw big rectangles up to the top of the function, and we would add all these up. Now, our answer won't be very accurate if we add up each one of these rectangles, right? Length times height, or base times height, but it'll give us an overall approximation for the area. And then what we can do is we can make delta x, the width of that rectangle, we can make it smaller, and we'll have more rectangles, so more addition to do, which is probably what you felt on that last example. We had a lot of squares to count up, a lot more work, but our answer starts to get a lot better. And as the slices approach 0, right, as they get smaller and smaller in width, our answer begins to approach the true answer. We would now write this as a dx instead of delta x, meaning that the slices are approaching 0 width. Of course, we would have this idea here of a limit. You would take the limit as delta x approaches 0, and that would give you your true area. So we would write this as the integral of fx dx. So this little symbol here is called the integral sign. It tells us what operation to perform, and the dx tells us the variable we're going to be integrating with respect to. Now, to do this in real, true mathematical form, you have to do a limit, and there's a bunch of complicated technicalities that we're going to gloss over for right now. And what we're going to do instead is we're going to take a bit of a shortcut. Usually, we, of course, have specific values for our calculation. And so these values are going to be the beginning and end of where you're trying to find the area, the a and b. So this is our final integral. We have from a to b, start at a, end at b, and find area. And that's a lot of adding. That's a lot of limits that we might have to do, but there's this shortcut. And the shortcut is that finding an integral is actually the reverse of finding a derivative. It's the antiderivative. Now, we haven't proved this, but it's actually called the fundamental theorem of calculus. The fact that integrals and derivatives are going to be opposites of each other. You'll prove that in a future class of calculus, but for now we're going to take it on faith that you can do integrals by doing antiderivatives. And so here we have the fundamental theorem. It's a very important, very wonderful theorem. It says, let fx be an antiderivative of fx, then the integral from a to b of fx is equal to capital Fx BA. Or you evaluate the antiderivative at B, and you evaluate the antiderivative at A, and you subtract the two values. Now there are some standard formulas for doing antiderivatives that hopefully you've learned by this point in the course. If you're going to do the antiderivative or the integral of x to the n, it's x to the n plus 1 over n plus 1 plus c. So let's look at an example here. We want to evaluate the integral, which we know is the antiderivative of x squared. So we would get x cubed over 3 plus c. Now again, that should make sense because if we were to do the derivative of this, the 3 would come down. We would get 3x squared over 3. The 3's would cancel, and we'd get back to our x squared. So this is the antiderivative of x squared. And because of the fundamental theorem of calculus, this is also the integral of x squared. So let's evaluate the integral of x squared from 0 to 2. So we do the same process, x cubed over 3. But now we don't need it to include the c anymore, and we only go from 0 to 2. So we plug the 2 into the top, 2 cubed over 3, subtract. Plug the bottom in, so 0 cubed over 3. And then just do arithmetic. So 8 over 3 minus 0, so 8 over 3. There's your answer. Let's try another one. We're going to do the integral from 0 to 1 of the cube root of x. Well, we definitely have to write this as x to the 1/3 if we're going to do the antiderivative properly. So we'll get x to the, what's 1/3 plus 1? That'll be 1/3 plus 3/3, so 4/3. Okay, x to the 4/3 over 4/3, evaluated from 0 to 1. So we get 1 to the 4/3 over 4/3, minus 0 to the 4/3 over 4/3. That'll give us 1 over 4/3 minus 0, which will give us 3 over 4. Let's try another one. We're going to evaluate the integral from 1 to 2 of 4x squared. Well, we get 4x cubed over 3 from 1 to 2, which is 4 times 2 cubed over 3 minus 4 times 1 cubed over 3. All right, well, 2 cubed is going to be 8 times 4 is 32. And so our final answer is 28 over 3. Now if we're going to do the antiderivative of 1 over x, we need to do ln x because the derivative of ln x is 1 over x. So let's try that out. The 3 is just a constant, so we can just put that in front. And we evaluate it from 1 to 2. Technically, I guess we should put another line there, 1 to 2. So we get 3 ln absolute value 2 minus 3 ln absolute value of 1. Absolute value of 1 is 1 and ln of 1 is 0, so that's just gone, and we get 3 ln 2. We don't need the absolute values anymore because the absolute value of 2 is 2. Let's do another one here. The integral of e to the x is, well, e to the x because the antiderivative of e to the x is e to the x. So this becomes e to the x evaluated from 1 to 3. So e to the 3 minus e to the 1. Well, I guess we could write e to the 1 as just e if we wanted, but we can't combine those at all. We need a calculator to get an exact value. Now here are some nice formulas for the trig functions. We know the integral of cos is sine, or sine is negative cos, secant squared is tan, and so on, because if we do the derivatives of these right-hand sides, we get back to that left-hand side. So let's try a fun trig one here. We have the integral of secant squared, and there's a 2, and we're going from 0 to pi by 4. Well, if we look at our list here, the integral of secant squared will be tan. So we'll get 2 tan from 0 to pi by 4. So that'll give us 2 tan pi by 4 minus 2 tan 0. Well, tan of 0 is just going to be 0. So we'll get 2 times 1, which is just 2. Now, some formulas are actually pretty difficult to discover. Trying to do the antiderivative can be challenging, and so calculus instructors will actually prove them using differentiation. So if you do the derivative of the formula, then you know it has to be true because, well, it was the antiderivative. So let's try to prove this formula here. So we're going to do the derivative of the right-hand side. We're going to try to take the derivative of that thing and see if we get back to the left-hand side. Well, we've got a product rule there to start off with, so 1/2 times root a squared minus x squared plus x over 2 times 1/2 a squared minus x squared to the negative 1/2 times negative 2x plus, well, now we've got this whole other term to deal with. Thankfully, the front is a constant, so we have a squared over 2. Derivative of sine inverse will be 1 over root 1 minus x over a squared. And then the derivative of x over a will be 1 over a. All right, well, now we need to simplify this and combine this, and apparently this whole thing should be root a squared minus x squared. Well, let's see what we can get. The front will be root a squared minus x squared over 2. Next up, we're going to have, well, one of these 2's will cancel with one of these 2's, and the x will make an x squared. So we're going to have negative x squared over 2. And then, of course, we could turn this into a 1 over the square root of a squared minus x squared. This, oh, one of the a's will cancel here, nice. A over 2, 1 over the square root of 1 minus x squared over a squared if we distribute that square. Okay, well, we gotta keep on trucking. Square root a squared minus x squared over 2 minus x squared over 2 root a squared minus x squared. And we want to clean up this portion over here. So I'm going to multiply that by a squared to get a little common denominator in there. So a over 2 root a squared minus x squared over a squared. Now, we should probably do this on the side a little bit here. If I've got the square root of a squared minus x squared over a squared, I can make that square root a squared minus x squared over square root a squared, which would be square root a squared minus x squared over a, assuming, of course, a is positive. So let's go ahead and do that. So we're going to get the square root of a squared minus x squared over 2 minus x squared over 2 root a squared minus x squared plus a over 2 root a squared minus x squared. And then we have over a. Well, that a is going to flip up to the top because when you're dividing, we're going to go ahead and flip it and multiply. So this a is going to actually flip up to the top here. Now, we're going to run out of space, so I'm going to make a little bit more room for us here on the page. So we're going to get the following. So we still have the 1 over 2 and the root a squared minus x squared. But now we have, well, I guess, x squared over 2 root a squared minus x squared plus a squared over 2 root a squared minus x squared. And it looks like these two have the same denominator. So let's go ahead and combine those. We'll get plus negative x squared plus a squared over 2 root a squared minus x squared. We'll keep this in the front. Now we could rationalize this because we're going to want to be able to simplify it. So we'll multiply by root a squared. I'll do that in another color. root a squared minus x squared, root a squared minus x squared, which will give us root a squared minus x squared over 2 plus a squared minus x squared times root a squared minus x squared over 2 a squared minus x squared. And here's the part we've all been waiting for. We can finally cancel out the a squared minus x squared. So that will give us the following final answer. Well, I guess one more step and then the final answer. Root a squared minus x squared over 2 plus root a squared minus x squared over 2. So 2 root a squared minus x squared over 2, which is just root a squared minus x squared. And so there we go. We got the same thing as on the left-hand side. Took a fair bit of work. It was a lot of algebra. But eventually, we took the derivative of this and found that it was equal to this, which means this must be the antiderivative. Now, that's definitely a complicated formula. But once we have it, we can use it to do an example. So I'm going to rewrite that example we had there. So to do this example, well, we just match everything up. The 9 is actually going to be 3 squared, which means that a is equal to 3. So we're going to get x over 2 square root 3 squared minus x squared plus 3 squared over 2 sine inverse of x over 3 plus c. Now, I don't expect you to be able to memorize that, but you have it handy, so maybe go ahead and highlight that formula, and we're going to actually use it in a little bit to come up with an interesting result. Now, before we do, just to really hammer home this point, area is created by the integral. And so the area bounded by a curve in the x-axis and the coordinate x equals a and x equals b is given by this integral. So whether we're looking at a shape like this or a shape like this, if we have the beginning and the ending of the shape and we have the function that goes along the top, we simply do the integral and we get that total area. So let's say we wanted to find the area under a parabola from 0 to 1. Well, you probably never learned a parabola formula in grade 10 or grade 11, but you learned how to graph a parabola. It looks something like that. And so we start at 0 and we go to 1. And so we're wondering, what is that area? Well, the area would be equal to the integral from 0 to 1 of x squared dx, which is equal to x to the 3 over 3, evaluated from 0 to 1, which is 1 cubed over 3 minus 0 cubed over 3, which is just 1 over 3. So if you've ever wondered what the area is, it's 1/3, and that should make sense if you imagine this as square here, because of course this is height 1. This would be half of a square, so 1/2, and the parabola is clearly less than that, but not a ton less. So we're getting 1/3 as our total area. Now let's use integration to prove the formula for the area of a circle. Alright, well, we need to draw a little diagram to see where our graph is and where our function is. So a circle would look something like this. And we're going to have a radius of r. So it's going to go r to the right and negative r to the left. Now, we need this curve along the top because we need that as a function. Well, that would be isolating for y in this equation. So y squared equals r squared minus x squared. So y equals technically plus or minus the square root. But we're going to take the positive square root, which means we're taking the positive portion. The negative square root is going to be the negative, the underside of that circle. Which means that our area, at least in the top portion here, is going to be equal to the integral from minus r to r of the square root of r squared minus x squared dx. Now that might look like a very scary integral, but we can use our knowledge from that formula we developed before. This is exactly that formula that took so long to work on. So we get x over 2, and then square root r squared minus x squared plus r squared over 2, sine inverse of x over r, and we're going to evaluate this from negative r to r. Well, that means we plug in r in the top, so r over 2 square root of r squared minus r squared plus r squared over 2 sine inverse of r over r. So that's our first portion. Then we have to subtract off the other one. So then we get negative r over 2, r squared minus negative r squared plus r squared over 2 sine inverse of negative r over r. All right. Well, let's simplify this as we go. R squared minus r squared. That's 0. And over here we've got r squared minus negative r squared. That's going to give us also 0. So that means we just have 0 plus r squared over 2 sine inverse of 1 minus 0 r squared over 2 sine inverse of negative 1. Okay, well, what is sine inverse of 1? What value do we need on the unit circle to get 1 from sine? The answer is pi by 2. So r squared over 2 times pi over 2 minus r squared over 2. What do we need for negative 1 from sine? Oh yeah, it's negative pi by 2. So we get r squared pi over 4 plus r squared pi over 4, which gives us 2 r squared pi over 4, which we could write as r squared pi over 2. Well, this is half the circle. So we need to double it up. So, double it up. Therefore, the area of a circle is equal to pi r squared pi over 2 times 2, which is your familiar pi r squared. And so if you've ever wondered why the formula is pi r squared, this is the answer. You do an antiderivative, you plug in all these values, you work out the algebra, and you get pi r squared. Now, this explanation hopefully shows you why we couldn't give you the formula, at least the proof of the formula, in grade 8 or 9 or 10. This is quite some advanced mathematics. It took humanity a long time to figure out the formula, and it was a lot of complicated math. So your teachers can be forgiven for not showing you a proof. It's quite technical. But now that you've proved it, I think it's quite remarkable that we need all these skills to prove, in some ways, such a simple formula. But this maybe shows you that it wasn't so simple after all. Now, just one final thing I want to look at here. What is the derivative of e to the x squared? Well, of course, we would get e to the x squared times 2x. But what's the integral of e to the x squared? What's the antiderivative? Is it possible? Well, the answer is that it is impossible. It's very sad. If you try, no matter how hard you try, the integral of e to the x squared, in terms of functions we know, is impossible. There is no antiderivative of e to the x squared. And the same can be said for all sorts of integrals. E to the x over x, or sine x squared, cos e to the x, 1 over ln x, all of these types of functions here, they're all pretty simple looking functions. But they don't have nice antiderivatives. In fact, the majority of basic functions don't have antiderivatives. And so this is something that you'll learn more in future courses. The examples we're going to do all have nice antiderivatives. But as you go further on in math, you'll find that doing derivatives is actually pretty easy, but doing antiderivatives or doing integrals can be quite challenging and can sometimes literally be impossible. Now here are your exercises. Make sure you try these. The answers are at the very back of the workbook. And if you run into any problems, feel free to let me know on one of our Google Meets or send me a message on Google Classroom or on the Remind app. Until next time, thanks for watching.